Oh boy. It's very loud. Blah, 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 blah. Oh, wrong mic. Blah, 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 blah. Okay. Here. Bears. Okay. Onboarding. Let's onboard. Does streamer read chat? I'm reading the chat right now. I'm not a streamer, I'm a professor. Professor streamer. Right? Professor streamer. Well, if I was on Twitter, I'd be Professor X then, right? Elon just sent up a poll saying, it was X a stupid name? We're like, yes, none of us are calling it that, right? I do like the domain, right? It's kind of cool. Okay, onboarding. What? Where's my checklist? Okay, we'll just do this one. Coffees, we'll need them today. Good job, friends, and thanks. Let's all thank the individual who brought us cookies. That was a real stand-up thing to do. Lapel mic is on. Cool. Can you hear me, class, in the real world? By which I mean cyberspace, right? That's the digital world. Yes, right. They're trying to shame me into reading the chat. It's not going to work. Can you hear me? Yep. Can you hear me in here, real life? No. I love incorrect answers. Spotlight, mute class, recording. And we can all see. That was the other. I'm not even reading these things. You can see? Cyberspace, can you see? Cool. Okay, now I'm going to proceed to ignore chat for forever. Okay. Hide floating meeting controls. Okay, what are we doing today? I forget. Okay, so today's the lecture on monads. Monads. What? TK Inter. Yeah, sorry about that. Uploading the wrong slide from the wrong directory. It's much more hilarious when I make the opposite mistake. When my 1000 level class starts seeing all of this stuff on monads, and they're like, is this going to be on the exam? I'm like, oh yeah, your exam is like 90% monad material. It seems that someone else must have been let out late. Okay, so monads. And it's like, at this point, it's not going to be that hard. And it's going to be like, well, what's the whole big deal about monads? This was sort of a little bit easy to understand. But I want to remind everyone that like we're week 10 of this functional programming course type of curriculum. So we're going to be able to understand this, but only because we've done like a lot of legwork. Right? But I don't want everyone to be so panicked about this because it's not going to be anything radically different. Right? So what did we do last week? Right? We talked about data. And then we talked about data that had substructure, like lists or trees or expressions. And then we asked about what type of patterns or like operations that we could have over those types of data, right? So it was something like this, a functor, right? You give me some type of structure, which is a functor, and you give me a function. And I can go inside of that structure and change the interior of the structure. Why is this important? This is like, oh, I can make a change on the interior of a structure without caring what that structure is. Right? When we're mapping, the function that you're mapping with is totally oblivious to the structure. That's important, right? Because we're just saying, walk into your thing, whatever that is, and make a change inside. Now, you may say, well, what's the big deal? We could always do this with pattern matching. But what we haven't yet dealt with is opaque types, or what are sometimes called opaque types. Types that don't have pattern matching. So what I/O is going to be is it's going to be a structure that's opaque. Right? We're going to be able to have an I/O wrapper, but that's it. We don't know what is inside of it. So we're going to need provisions for reaching into structure and making changes inside that structure while not caring about what that outside structure is. So I do want to be clear about something, right? So because this was the only functional programming course you were ever going to take, I had to make a decision about breadth versus depth, right? And because this is the only functional programming course you're going to take, I opted for breadth. So I'm trying to teach you all of the things, but we're not going very deeply into any of those individual things. This whole course is sort of like, you just need to have like a good enough understanding of stuff. Like you don't have to be lambda calculus experts, but you do know how to evaluate simple lambda calculus expressions. In the same light, I'm not going to go really into what these functors, applicatives, and monads mean in terms of like sequencing and error handling. I just want to get us to a point where we can like understand that a monad is just another type of class instance, which is super useful for working with I/O through something called a state transformer. Right? So I'm not really going to ask you anything about monads on your exam, aside using one, using the do notation. That's the learning objective for monads. Be able to use the do notation. And that's it. Right? And then we'll do a little bit of I/O. But I appreciate that the next few, this lecture and the next lecture may be fairly heavy. And if we wanted to go into detail about any of it, it does get rapidly sophisticated. So we just need to get a good enough provisional functional understanding of this so we can basically use the do notation. Okay, so that being said, we have these functors, right, which was you give me a function and something with structure over A, and I give you something structure over B. This was an applicative. Okay, now I give you structure over a function, and you give me something with structure, and I will return something with structure. Right, so this is I'm putting the function inside. What this effectively is, if you start reading about this, I didn't really talk about it that much. This is the technology required to get sequencing back into our system. Right, this is sort of hard to grapple with. A TA that we had last year, Miss Hayes, very, very clever individual, wrote a little primer about applicatives versus monads that we're going to post, and you should read it. Because I'm going to present a conceptualization of monads that I was taught and I understand, but that's not the sequence way of understanding it. So this TA wrote a different way of conceptualizing the same thing, right? So the applicative really was an operator that we introduced in order to get sequencing back. What we're going to introduce today is this bind operation, and what this bind operation does is it operates over data which forms a monad, right? So the same way that we can have a functor for data that forms a functor, or an applicative for data that forms an applicative functor, we can have this bind operation for data that is considered to be a monad. Technically, this is the reverse bind. I just want to, this is the best way to sort of compare everything, right? So what does a bind do? Well, it's a bind. I give you a function that goes from A to something with structure over B. You give me something with structure over A, and I give you something with structure over B. Okay, good. He was who I was looking for. So we'll pause in a second. Okay? So this is what we're going to be focusing on using today. Right, except this is the reverse bind. Okay, so let's pause on that. Okay, so Mr. Field, we were talking about you a moment ago because you've been so helpful on the EdStem. That's number one. Number two, I've noticed you've worn a Canada shirt every week, right? Every week. And he only has 2 of them, right? So this is deeply concerning for me. So in order to thank you for all your help and to help you overcome some hygiene concerns, I've brought you this. Right? So now you don't have to wear your shirt anymore. You can just wear a scarf. Yeah, okay. So thanks again, yeah. Just such good vibes from the class today. Everyone's just so warm over monads, really warm. Leafs won last game, yeah, I'm well aware. So they're no longer very trash, just somewhat trash. But this is what the Maple Leafs do. They're good, and then they're trash, and you hate them, and then they do something, they make some remarkable comeback, and you're like, no, they can do it again. So my prediction, they'll lose in overtime in Game 7. That's the most, which is the thing that happened last time we went up against Boston and the time before that, right? So I am predicting Game 7 loss. I'd be happy with that effectively. But yeah, tentatively go Leafs go. Okay. So here's the definition, right? So if we wanted some data which was a functor, we were obligated to define this, a map operator. This is the infix map operator. If we wanted to define a applicative map for a piece of data, we'd be obligated to define these two functions. A pure function, which is effectively just a function that gets you into the structure, and this applicative functor or starship operator or eye of Sauron, whatever you want to call it, right, which does this. And we played a little bit with this last week, right, because the main thing about utilizing these applicatives is that we get sort of the applicative is something that can help you with error handling, but a specific type of error handling, a short circuit type of error handling, right? So we can do something like this. Okay. Jesus, this subsystem is sometimes very slow. Okay. We now have a way where I can say, oh, okay, like add to, like if these may be integers. Whoops. Okay, but like this is handling errors for us, right? The same was true if I were to start using the union monad, so left error right, I'll say, or maybe error 2. And I could say this was what, right 1? Right, so that should give us error 2. This should maybe give us right 3. Okay, but here is the issue for applicatives. Error 2, error 1. Okay, so this is what we want to happen. Left is an error signal. But it said, oh, I detected an error signal. Computation is done. So I gave you a question a few weeks ago that said, hey, what happens if you wanted sort of like all of the error messages to be lifted up? How would you do that? And if you tried it, you probably would have found out that was really difficult, actually, to collect all of these error messages in a list. An applicative can't do this. An applicative wouldn't be able to say, here is the list of all of the errors that you've generated during this computation. It can only short circuit when it hits one. A monad can do this. Right? A monad is something that's going to be able to collect all of the previous calculation and act on it. Right? So one way of thinking about this bind operation, right? So let's just look. What does a monad have to have? Well, it has to also be an applicative and therefore a functor. It has to have a return function, which given A puts structure over A. What does return look like in this situation? What is return? It's just pure. In fact, if you look at most monads in the system, it's just going to say return is equal to pure. So the Haskell people are actually arguing about removing return from the system for two reasons. It's an overloaded term from imperative programming, which means something totally different to what it means here. And pure already exists in the system, right? So if you see return, you can always just think pure. It's probably better to think pure, just so we're not getting confused. Okay, so this is the actual bind operator. The one I showed on the previous slide was the reverse bind, just so we could like line up a bunch of the structure. But this is how it's sort of actually defined in the system. And I like thinking of, I'm going to try to explain this in a variety of ways, but the way that I sort of understand this bind operator is that you have something with structure over it, and you have a function that takes something from the inside of that structure to the same type of structure with something else on the inside. So it's kind of like I want to evaluate this here, but it doesn't quite fit. Right? So I like to think about it as it's like the shove operator. It's like you don't quite fit, but go. So, okay, so what do I mean by this? Let's look at the type of this bind operator. It's like that. So I'm going to just tell you, maybe is a monad. That shouldn't be too much of a surprise. So I should be able to do this with a maybe. So I can take something like just one. That's this. And I should be able to push it into a function which takes x and then maybe goes to just x plus 1. What? Oh, yes, thank you. Okay, you see how like this function doesn't quite take this because it's ignoring the structure? So one way of conceptualizing this is the way that I conceptualize it, is this is just sort of like an operator where like you push it through this pipe and it comes out the other side and it fits into that function. We've shoved it into that function. That's one way of thinking about it. Another way of thinking about it is that this is the future, this is the past, this is how you make one step from the past into the future. Right? If you want to think about monads aiding us in sequencing, that is the way of looking at it. I don't want to go too deep down any of these rabbit holes because the more details I give, the less sense this all ends up making. Right? This is the level that I want to understand. Okay? Are we overwhelmed now that I've said, look, we have a monad, and all a monad is a class instance with these two functions? That doesn't seem too, like this is basically what we had for functors and applicatives. It's just the next thing in that chain, right? So defining it should be fairly straightforward. Maybe utilizing it is a different story. We have already used data types that are monad instances. Basically everything that we've been using is a monad instance. Either is a monad, list is a monad, maybe is a monad, partial function application is a monad, and importantly, I/O is a monad. And what's important about I/O? I/O is the structure that admits no pattern matching. That's the trouble. If you wanted to get any, you can't remove anything from the I/O structure for good reason. So we're going to need provisions for jumping into the I/O structure and making changes. So this infix operator is called bind. I'm very happy that it actually does get a name that I can state out loud. We use this bind operator to okay, so this is how I see it. You have some type of structure, and it's encapsulating something. The bind operator allows you to jump into that structure and make changes according to some computation, and then leave. Right, so the outside doesn't change, but the inside changes. And this is all being done oblivious to the structure itself. Remember, in a monad, I have to go from A to MB. So I can define a function that doesn't care. I can be oblivious to the structure. I just tell you how to manipulate it. Okay, so for example, as I showed you, we can reach inside the just X and operate on X. This may not seem very exciting, but we'll soon see that I/O is a monad, and there it becomes effectively critical. Right? This is the reason we're doing state transformers and monads, is in order to make I/O functionally pure. That is going to be the punchline, not monads necessarily. Okay, so let's just look at how the maybe monad is defined, right? So we need something that takes something that's from maybe A, and then I need to be given some function like this, and then I need to be given that back. So this seems pretty clear what we should do. If we're given something from maybe A, what I want to do is reach into it and then send it through this function. So that's what this is doing, right? So we're not nothing, right? So we can match just X. So I'm saying grab that X out and then put it through K, and that should type properly. That should give us maybe B. If you see nothing, then this is the failure case. Just send up that failure up the chain, right? We're still going to want this automatic error handling in our monads. And what should return be? Well, pure. Right, so now we can do things like this. I take just one, and I'm like shoving it into this function that doesn't take a maybe type, but takes an integer, but nonetheless, it still works. I can take nothing and try to shove it into this function, and you get nothing back. That's fairly strange, right? Because this wasn't even typed properly for nothing. Right? So error handling is still something that we get. So the behavior on nothing may seem strange here, but remember, nothing is typically encapsulates an error state, and short-circuiting out or pushing that up the chain is what we want. And sort of the reason the monad is different is because we're going to be forming like a chain of these binds, and the errors are going to be present within this chain. Write a function maybe increment that increments a maybe integer. Okay, we can do this in a bunch of ways. Okay. Maybe increments. I want to take a maybe let's say maybe integer. We want to go to a maybe integer. Okay, so one of the ways we used to do this was just say this. Maybe increment of nothing is nothing. Maybe increment of just x is just x plus 1. Okay, so that's with pattern matching. Let's just see that this works. What? Oh, I haven't loaded anything. Yeah, that's a good thing to do. Okay, that was the sort of pattern matchy way of doing this. We have an applicative way of doing this as well. I can say add plus 1, map this to the applicative. Oh, no, I can't do that, actually. We'd have to do this with the bind. Right, so I take plus 1, and now I shove it into a function which takes x and goes to just x plus 1. Okay. So, oh, yes. What am I doing? I want to take mx. Right, yeah. Okay, just 2. So this is now with the bind information. Okay, that's not too interesting. What is more interesting if we write a function that adds a maybe integer to a maybe integer. Okay, so let's do that in all of the ways. And I'm going to do this in various parts. So maybe add, that's a maybe integer with a maybe integer with a maybe integer. And we can say maybe add of maybe x and maybe y is something. And then, maybe add of, we'll do it the most basic way first. Just x and just y is just x plus y. And now we have to do all, okay, so really here we just have to say this. That catches all of the error cases. But so I can make a point about something. I'm just going to code them. Okay. So this should be working. Just 1. Just 2, to get just 3. Okay, so that's the pattern matching way of doing this. And every time, if I wanted to add 3 integers, then you always having to keep adding these edge cases and edge cases and edge cases, which is something that we want to avoid. We solved this provisionally last week, right, by doing this, maybe x, maybe y. This is adding together maybe x applied to maybe y, right? And this is a Haskell program in the applicative form. It's relevant here that this is a one-line solution to this problem, right? Because I'm going to complicate this in a bit, where we're going to be able to use an applicative for like one branch. But here we've like totally implemented maybe add by doing this. Okay, let's now do this with a bind. We're going to have to be clever about what we're doing here. So how do we want to do this with a bind? Well, I need to push 2 things into something that's going to get x plus y. But we don't have bivariate functions in Haskell. Remember, everything's a univariate function. So I have to use 2 binds in here. Right? What 2 binds are that? So I need to take maybe x, and I need to shove that into something that takes x to something that takes maybe y, and shoves that into something which takes y and goes to, x, just x plus y. Is this very beautiful? You can be honest. I wouldn't say that that's very beautiful. But it works. It's the applicative form. Or sorry, it's not the applicative form. This is using a monad now. That's what we're doing. We're using the bind operator. Okay, so here's the punchline. Okay, so the bind is a left associative operator. Oops, info, not type. Okay, left associative. That means these brackets can come off. Okay, let's also let's do a little bit of moving around. Okay, does this still work? Sure does. Does it add these 2 things together? Sure does. What is this is beginning to look like? Has anyone stumbled upon the do notation? Yeah, you all laugh because I know you all found it. Okay, this is the do notation, okay? Do notation is syntactic sugar for this. It's so close already. So all I'm going to do is write do here. And this is going to tell Haskell, hey, I want to write these lines differently so that they're not ugly. Okay, is this ugly? No. How dare you even suggest it, right? So this is how you sort of have to read through these do's. You don't have to. This is how I interpret these do's. This is going to be, we say do, and you say, okay, the following things are going to be a sequence set of actions. And maybe I shouldn't. Okay, hold on. I'm going to do this. I'll say that this is maybe add prime. Whoops, no, hold on. First, I want to get this back, that back, and then I'll put that there. Okay. So do you see how we can sort of sequence things in functions? The fact that we're taking x to something that takes y to something that takes z to something, that's a sequence of stuff. So that's how we can force sequencing back into a pure system, by exploiting function evaluation, right? Someplace where we know there's going to be an order evaluation. So that's exactly what lines 5 and 6 are doing. I'm going from x into something that takes y into something. Right, so the first thing we have to understand about do's is that, no, these are sequenced actions now. I can't really reverse lines 5 and 6 and maintain the same behavior. Right, so do briefly gives you a set of sequence actions. The second thing that this do does, and what this arrow is doing, I like to think of this arrow as extracting something from inside something with structure on it. So I'm saying mx, you are something with structure over it. Your structure over x. I don't even actually care at this point what that structure is, but here it's maybe, or a jest. So I'm saying reach into that structure, pull it out. Then reach into the other thing and pull it out. Now operate on the things that I've pulled out, and then put the structure back on before I send it back up. Right, because what could this be replaced with? Okay, so return, is return doing the same thing that it does in the imperative language? No. It's just putting structure over stuff. Like we could return anywhere, really, where we're working in the presence of a monad, but if we were using pure, that would even work for applicatives. Okay, why would we want to use return instead of just? Yeah. Yes, I'll give both of you points. It's more generic. If I remove this, can you determine what the typing is of this maybe add prime function? Before I show you the type, let's just investigate it. So I'm saying this will work over anything that's a monad, right? What did I say were some things that were monads? Yeah? List. It will make sense once I show you what the list monad is. But this is effectively list comprehension, or like adding over the Cartesian product of those things, which is what you would want. You're going to work with a more sensible definition of list applicative on your homework. What else did I say was an applicative, or was a monad? IO, okay, I can't do IO yet, right? We've got to wait a couple, huh? Either, yeah, so let's do either, right? Write 2, write 3 with write 5. Okay, because what did this do? In the case where I'm giving it an either, the structure over it is write. I'm saying reach into the right, pull out the 3, reach into the other right, pull out the 5, and now add them, and then put the structure back on. We were able to briefly take things out of their boxes in a controlled environment. But the only rule is we have to put everything back into the box before we leave. Right, so it's like showing up to a monad party, but like you really do have to structure yourself in order to go, and structure yourself when you leave. But all bets are off when you're at the party, kind of. This isn't even the most bizarre description. Is anyone following along with Learn You a Haskell for a Great Good? Yeah, his description of an IO'd monad, man, that is something else, right? He describes it as a box it's like a centipede box. It's like a box with like legs on it that you like send off into the world. It like scurries away like a centipede and then comes back. Seriously, It will make sense once you read it, but it is quite bizarre. Okay, so now we have this maybe routine that's going to work over anything that's a monad. So what is its type? Yeah, give it a go. Okay, we got to have a monad M. Well, are integers the only things that we can add? Right, okay, so we need structure. That's the first thing we're going to have to derive from, and that structure has to be a monad. So that's the first class instance. The second thing we're doing is adding things together. So we also have to be in a type which permits adding, which is the number class. So this is going to be, we need structure that's a monad. We need types that are numbers. And provided that we've satisfied that, then this add routine takes you from monad structure over B to monad structure over B to monad structure over B. Does that make sense? Yeah. Maybe integer, maybe integer, maybe integer. Did that make sense for like the either one? Yeah. You wanted to go from either integer error to either integer error to either integer error. Did that work for the list one? Yeah. You want to go from list to list to list. That's what happens in each case. Right? So you can regard the do notation as a way to reach inside of something and pull something out and manipulate it before putting it back. That's how we can regard these things. Okay. So that's just what I said in the slides, so you have it. And this is the big important part, right? That the do notation is just a syntactic sugar for those binds, right? Which gives you yet another correct answer for question H on your exam, whose question is, give me an example of syntactic sugar in Haskell, right? The do blocks would be a totally fine answer there as well. Okay. What's the big deal? Couldn't we always do this? We could do this with applicatives. It's like one of the first things that I typed, right? So why did we just introduce a tool that doesn't seem to do anything? True. Okay, but what is relevant in this example is that there was no subcomputation that was failing. Right? The failures were always at this level. MX was either always a just or a nothing. Right? We could always immediately determine that an error was caused. Let's change the problem to something like this. I'm going to set a trivial data structure up which will allow us to have subcomputation that can fail. So I'm going to say, let's have an expression. And my expressions are going to be comprised of values which are integers or the division of two expressions. And I want to write something like eval along this. All right? Given an expression, I want to return an integer. And I want to do something like this. Right? I want to say, if I evaluate a value, that's just the value back, n. If I evaluate this division expression, just evaluate the expressions themselves into integers and then divide. However, we can't divide by 0, right? So where can I tell Haskell about this problem? In this code. Right? This is now what I want to resolve. I still want this. Right, so we're just going to have to like add in all of our copes. Right, so first, what's the first cope here? Well, this won't work. Okay, so what would you do in this situation? What's the first thing that comes to mind? Okay, so we need a safe division algorithm here. Right, so you give me two integers, and I maybe give you back an integer. Right? And if you're trying to divide by 0, then you get nothing. That's the failure condition. And otherwise, just return the division of those two things. And specifying failure cases is fair. Like we're trying to generalize all the things. Every time we have an edge case like at 2, we should be thinking, hey, how can we generate an edge case? I don't want edge cases. Those things stress me out. But it's like, well, how else is Haskell supposed to know that this is the error case in this situation? Right? So I don't think there's my point is, I don't think there's any way of automating the fact that this 0 is going to throw some type of problem. Okay, so does that solve the problem? Can I just give safe division now to the safe eval routine? Well, this is a new, okay. So eval went from expression to integer. So I guess we can't have that. So maybe we need a safe evaluation routine that goes from expression to maybe integer. We have a safe evaluation which returns a maybe integer. So is this okay? Will this work? What is the type of safe eval? What is the type of safe eval? Integer to maybe integer. So what is the type here? It's a maybe integer. So is this typed properly? No. This is typed wrong. We have a safediv function which goes from integer to integer to maybe integer. But what we really need is maybe integer to maybe integer to maybe integer. Right? So this is what I'm trying to show is like things are rapidly unraveling. Right? As soon as we introduced error handling at the output, it is now infecting the rest of the chain here. Right? Now maybes are going to have to be sort of everywhere. Okay. So maybe we could try to use the applicative form to sort of applicatively map the safe div over this. It's not going to work either. If you want, you go home and convince yourself that this isn't going to type properly. So what we really do need here is like a maybe divide in the same spirit as our maybe add. Okay, but here's the difference. This is the maybe divide. So is this implemented in one line? No, because we introduced an edge case at 2. I don't want to have to introduce an edge case, which is outside of the applicative. I want all of this to be implemented by one line, by the applicative. Here, we can't do it. Applicative cannot cope with doing this zero check inside. Okay, so if we did this maybe divide, then we could implement safe eval as following. But again, I don't like the fact that we had to generate an edge case at 2. And if we wanted to try something else, like do some type of branch computation, that's off the table too. Okay, so now the question becomes, how could we have done this with monads instead? And does it simplify things? So let me just go grab this. Okay. So I have this type of data. Oh, I'd have to define the monad. So I can't actually do that. Okay, so I'm telling you that hold on, let me think. Oh, no, this should work. Okay, hold on. So what do I want? I want a safe eval routine that takes a, okay, hold on, let me think. Yes, it was expression to maybe integer. Expression to maybe integer. Okay, so how can I get the safe evaluation here? What is this going to look like with the do? Right, so we have 2 cases here. We have cases where this is a value and cases where it's a div. Is that how I did it? I have to remind this is always a very tough lecture to do. Yeah. Okay, so I'm just going to do it like this. Val x is just x. And how do I safe evaluate the division of expression 1 and expression 2? We're going to use the do. Do reach inside expression 1 and grab the integer that's there. Right? Grab the integer that is encapsulated by expression 2, right? And grab the integer that's there. Or I've tried to extract from a nothing, in which case error handle that all the way up. Right? So if this fails, that's fine. It's going to automatically return nothing at this point. Okay, so I have x and y. What should I do now? What's the objective here? I need to return what? Just the division of x and y? It's close, but not quite. This is going to work. Oops. Yeah, have I lost my mind? But this should, oh, I'm a moron. Safe evaluate that. Safe evaluate that. Yeah, because that will turn it into a maybe integer. Okay, cool. Sorry about that. All right, so this is kind of working. I can do safe eval div val4 with val2. But if I do 0, we still get that exception. So I say, what do we do? How can I fix this now? Something I told you not to use at the beginning of the year that now we have to use now. If expressions, right? I can say if x is 0. Oh, y, yes. Y, oh, y, oh, y, oh. Then nothing, right? Else that. Okay? I know, it's now, the syntactic sugar is deliberately provisioned to make it kind of look like imperative programming. You wait till I show you how easy parsing is in Haskell, right, using these types of extractions. But now this is going to work. And like more than that, we didn't have to return nothing. I could do other computations. We could try something else. We could dispatch. Like this is really the important distinction between monads and applicatives. The fact that I'm like, oh, I know that this is an error case, and now I can actually make decisions about it. Like when I was extracting from here, if seval, if that evaluated to nothing, can I dispatch against that? No, the monad just says, we're short-circuiting out of this. That's like how all of the applicative and monad has been defined. As soon as you touch a nothing, the whole computation is nothing, right? So I can't, like, either we get an integer from this, or this whole function returns nothing, right? That's why this if statement is a little bit different. I am detecting a degenerate case and acting on it, right? Rather than just having the monad do some type of automated exception handling. Okay. So if you wanted to do the same thing using binds, this is how it would look like. I sort of de-sugared it, right? How do I safe evaluate div x and y? Well, take safe eval of x. That's going to give you a maybe integer and shove that into a function which takes m, its inside, and gives it to something that takes the evaluation of y, which is a maybe integer, and shoves that into a function which also takes the inside of that, and then does this. Right? That behavior. This is weird, right? Because like this if expression has to be at line 6. Right? Normally we're used to like being able to permute lines because equal means equal. But here, remember that implicit in the do notation, right, is the fact that we have this sequence of x goes to thing, goes to thing, goes to thing, right? So that it is properly a sequence. So notice we can catch these degenerate inputs and branch on it. Rather than and then try something else. This is an important distinction from the applicative that can only short circuit on errors. Okay, so I just want to show you. So really all we had to understand about monads is it's just another class instance. It's another class instance which gives us a bind operator, which gives us access to a syntactic sugar of a do notation, which gives us a brief period of time where we can sequence actions and pull stuff out of their structure. That's really the relevant thing. I can go into I/O and take something out. What I need to now tell you is actually like how to actually make something an instance of a monad. And it's the same thing as a functor and applicative. You just need to define the appropriate functions, and these functions have to satisfy certain laws. So now I'm just going to show you those laws, right? So to become a monad, you also need to be an applicative. Which means returns kind of free. That's just pure. And you also have to implement this bind operator. And the bind operator has to satisfy these monad laws. I'm never asking you to prove anything as a monad. That is a little bit outside now of what I expect everyone to be able to do. But I can still sort of explain what these mean, right? So the first one, we have left identity, right identity associativity of these binding operators. But I think it's best to look at them through the do notation. So I rip this off of the Haskell wiki. And this is how they're trying to conceptualize some of those monad rules, right? So the first one, left identity means if you put structure on something and then then pull it out of its structure, and then if you have x, you put structure on it, and then you extract it, and then you say f over that. That's just the same thing as doing f of x. Right? Putting structure on something and then taking it out, that's like an identity operation, or that's like an inverse operation. Right identity means if you like extract something out of M and then return it. So like take the structure off of M, or X has structure on it, take it off, and now put structure back on. Those are also inverse operations. You're just returning M. Associativity is a little bit more complicated, but it's effectively saying it's no problem if you want to like switch some of these lines. And we're not really going to have to engage in this too much. I just want to show you this for like completion's sake, right? So again, because if you wanted to come up with a new monad and then prove that it is a monad, you would have to prove these rules, right? And you'd be capable of doing it. They're just a little bit trickier than like proving the applicatives and other things. But you have the tools, like the structural induction or Yeah, so on your homework, what I've asked you to do is prove one of either's applicative laws. And so make sure you're not using structural induction when the data I'm giving you isn't actually recursive, right? So just be careful about that. Okay, so the real interesting thing here is because Haskell doesn't care about order, and because of mutual recursion, you can actually use the do notation to define the functor and applicative. I know that this is strange, but it's okay. It's just mutually recursive. Like, if bind uses functor and functor uses bind, that's fine. I've shown you mutual recursion is something that is in our tool set, as long as everything is being called with smaller input. And it is often the case, if you use the do notation, defining the functor and applicative become really easy. Okay, so I'm telling you that the list has a monad, or is a monad, and therefore we can use the do notation. I don't even care how the monad has been defined. I'm just assured that I can use do notation. So what does the map operator mean here? How can I use do for that? I'm saying, well, what does it mean to map F along A's? Reach into the list structure, pull the thing out of the list, and then apply F to it. Is that not what a map does? Right, so there you go. There's the definition for map using the do notation. What about an applicative? Well, it was hard to sort of even demonstrate what applicatives were doing last week, but it's sort of more clear what they're doing with the do notation. I'm going to give you a list of functions and a list of values, and I'm saying take one of the functions, take one of the values, and return that function applied to that value. Right? And that's going to be the definition of the applicative. If you're curious, this is the definition of the list monad. Right? So the list applicative is primed to do Cartesian product. Right? This is why it's sort of bizarre. Right? You're going to, on your homework, you're going to be working, and you should have worked with the zip list data in one of your tutorials. Right? There's actually two applicatives and monads that we can define on lists. It's just Haskell chose sort of the more strange one. And you can only have one functor, applicative, and monad defined for any data at any given time, right? Because Haskell needs to know if you're using the applicative, there can't be more than one of them, okay? So, but this is how the list monad is defined. It's defined using list comprehension, right? So to bind x's into f, that is to extract out of x's, extract out of f of x's, and then just list all of these y's, right? And if you're really curious, so I just learned this year, actually, that the arrows in here aren't actually from a monad. If there's many things that are obnoxious about Haskell. One of the most obnoxious things is this use of syntactic sugar, right? Because there's lots of overloaded symbols, for example. Like, you know, the empty list is also the constructor for, like, the list constructor. There's a lot of things that can be confusing. So this isn't actually do notation. This is list comprehension notation. And this list comprehension is actually a syntactic sugar over a set of if expressions and concat maps. Right? So I can show you how to do list comprehensions as almost like a straight line program. Like just, well, not really. I can show you how to do a list comprehension, and we only need an if expression and a concat map, right? A function that sort of looks like this. Right? If you give me a bunch of lists, I can like return to you the super list of those lists all concatenated with one another. Okay? So the only thing we need to understand, though, is things that are monads have a bind operator. Things that have a bind operator can use the do notation. And things that use the do notation allow us to reach into the structure and pull stuff out. That's really the level of understanding that we have to have here. You don't have to understand monads any more than you understand functors or understand applicatives. They're just going to be a tool that we're going to use for doing I/O. Right, so again, the learning objective is just to be able to use the do notation a little bit. Okay, so no break. You have cookies. You should have enough sugar and coffee. Let's talk about this state. It'd be better if I can let you out a little bit early. I have to go to some type of open house after this. Okay. So we have monads now, which is just another class instance, right? Functor applicative monad. right? If something is a monad, we have bind, we have fold, we have applicative. I want to now design a new data type, and this data type, we're also going to have to make a monad, right? So I'm going to define new data, and then we're going to define all, like a bind operator effectively to make that data also a monad, so that we can use the do notation on that new data. Okay. So one of the problems, what was one of the problems in tiling? One of the difficulties? So you had to number the tiles with unique integers, right? That was a little bit of a problem. So what were some of the solutions that you guys used for using unique identifiers? Yes? What? Like how many did you? I don't understand how that helps you label anything, though.
I get the number of tiles I need for each triangle, and then that forms the sequence, and I know the biggest number from the previous triangle, so I can use that to.
Okay, did it work?
It did work.
Cool. What other type of, yeah? So you look at the previous tiling and ask for its largest number and increment by 1? Yeah, you have to look at your tiling and look for its max. Okay, so you're sort of like, you're just looking at the previous recursive call and, okay, yeah, up there. Shh.
I passed the max number of tiles through each of the functions, but then multiplied that by, got the first triangle, got the bottom 3 triangles, but then multiplied that number, well, added that number to, added the number of the tiles in there to that number, then 2 times that number, 3 times that number, to kind of.
Yeah. Well done. These are all really neat solutions. Here's mine. Okay. All I did was give another input to the tiling function, and it was a list of numbers. And I'm saying whenever you need a number, take it from that list. And whenever you recurse, break that list into 4 pieces and give that one of the pieces to the list. So does that guarantee unique tiling numbers? Yes, because they're all coming from the list. Do we know how many tiles we need ahead of time? Yep, 4 to the power of k minus 1 divided by 3. Okay, so what I'm saying here is that suppose I gave you a function that, if you called it, was guaranteed to give you a new integer. Would that have been helpful for tiling? Yeah. Okay, so the solution that I had, and like in all of your tail recursions, do you know how I said we can't really have global variables or state? That's kind of a lie, right? You can if you can use the inputs to any function to hold an arbitrary amount of information. So if you wanted a global variable, that's just a matter of like saying, all of you get access to like another variable in your input. And this was effectively, like in my tiling solution, passing along that list was effectively like giving everything access to like a global state of stuff. What I want to do is accept that this is something we're going to do all the time. Like use part of the inputs to pack information. And when we do this, what we're effectively doing is simulating state. So what I want to create is some provision for doing a state transformation, right? And that's what we're going to learn today. How do I have a function that, in addition to having a function, is also allowed to pass along extra information as part of its inputs? Okay, so here's our motivational example. I'm going to give you a tree, this tree, simple binary tree, right? It only has leaves. And what I want to do is I want to write a function label that labels this tree with unique integers. Can we do that? Let's try to code this up. It's a little bit tricky if you don't think about it properly. Okay, so let's do this. So there's a tree. I want this. Okay. this a bit. I'll call that undefined. And I have a tree, and we want to label it. So there's the tree in here, I believe. So I'll say here's a tree. Okay, so how should we tackle this? Okay, so what did I recommend? Okay, we're going to use another we're going to use one of the input variables to help do this. Okay, so I'm going to say let's have a helper function, helper label. I'm going to take a tree of A and an integer, and I'm going to let's just make this an integer. And we're going to turn a tree of integers. And this is going to be, I'm going to say this is the new label. When you need to label something, use that number. Okay, we're going to call it fresh. Okay, so if I have h label of a leaf of A, and you've given me this fresh integer, then I'm just going to say, oh yeah, leaf of fresh. That's how this works. Okay, however, we need to return two things. You give me the integer to use, and I have to give you back the next one to use. That's the agreement. I return to you output and the next fresh integer. That's how we can solve this. Okay, so I'm going to return leaf of fresh and fresh. So that means our initial call here to hlabel is going to be, I take this tree, I label that tree, I start counting from 0, and then I just want to take the first element from it, right? Because that's this part. Okay, so do we agree that if I were to call hlabel, leave, all of you, leaf, okay. Hlabel, leaf of, hold on, yeah, A, start labeling from 0, that should return to me leaf of 0, oh, fresh plus 1. I'm an idiot. Here. It's a good thing I'm doing debugging. Okay. So I'm saying label this leaf. That's the integer. That's the new integer that you should use. There's the tree label, and there's the next integer that you should use. This is the next fresh integer in the sequence. Okay, so this was the easy one. This is the harder one. Node, tree left, tree right. Okay, so I can sort of start setting things up here. Oh, and we have a fresh integer. So I know I'm going to want to return node of t left prime, t right prime. This is going to have to be a tuple. Some integer is going to have to go there. 1, 2, 3, 1, 2, where TL prime a number, TR prime a number, something like this. Okay, so I know for sure I want to label the left tree, but I need to know how do I thread the fresh integer through this? We have to be careful about the order that we do this. So how can I start resolving these things? Like, should I put fresh plus 1 here? No, because obviously we could have required more than one extra. I don't know what has yet happened in my subcomputation. So that's really the tricky part here. I can't do this yet. I don't know what goes there. So let's see. Maybe I can say, right tree, you start. I have this integer. I know no one's used it yet. Why don't you start from here in my right tree? Then you're going to come back and you're going to finish doing what you're doing. And when you're finished, you're going to pass me the relabeled tree and the next number to use. Is that not how we set this up? Okay, so that number should be bigger than any of the numbers in the right tree at this point. So that means I can start labeling the left tree starting from that number. And it's going to do its thing, and it's going to return back a new fresh integer that's larger than everything now in the left tree, which means that I can go up to here and say, okay, yeah, this is the next one that you should use. Do you think this will work? Let's give it a go. Usually a good sign. H label t, oh, and 0. Yeah, 0, 1, 2. Unique labels. I can even try, let's try being a little bit more. So I can say I have S, which is a tree which connects T and T. I'll be a little bit more complicated. Node. There's S. Let's try to label S. Yeah. Yes? You're correct. I only need to add 1 here. Is that, did we skip something? Oh, is that where we're missing a 3? Yeah. Okay. But you see how I had to like really carefully thread this fresh variable through the function itself? I don't want to do that. I want that to be automated because I'm going to screw it up whenever I do it. And it's good to try and automate the things that you screw up. So what exactly did we do? Okay. We just modified our algorithm so that instead of taking A and returning B, it takes A and a state and returns B and a new state. And this is exactly what we want a state transformation to be. Okay? Instead of having a function that goes from A to B, I want to have a state transformation over that, which means I have a function which takes A and a state and returns B and a new state. I have like so many pictures about this, so it will make sense. So the notion of holding state can and should be abstracted away. We expect to use it again and again and again. We want a state transformation data type. We're going to call it ST for state transformation for defining functions like fresh. Like so fresh, like a function that always gives you a new integer, would be super useful here. Do you agree? So suppose I had a function that was a state transformer that was also a monad that allowed me to do this. Every time I pulled out a fresh, imagine that you're guaranteed to get a new number. That's how it's set up. I could therefore write the same program that we just wrote and bypass all of this threading in the following way, right? Provided that we can make a state transformer a monad, which we'll do. So how do I label a leaf? Well, it turns out I don't actually care what's there because it's going to be replaced by a number. So label this leaf by entering the do notation in the monad. Fresh is a state transformer. Pull out a new number. I'm guaranteed from you to get a new number, and I'm going to return leaf of that new number. It's guaranteed fresh integer. What does it mean to relabel a generic tree? Well, label the left tree and pull it out, that left tree. Label the right tree and pull it out, and then put a node over them. Because here what we're going to be doing is these are going to be state transformations. Right? So when we're pulling out here, what we're doing is extracting the tree from its state transformer. This will become much more clear with examples. But it would be, this doesn't yet work. I'm saying, wouldn't it be nice as an objective, right, if we could devise a state transformer data type which was a monad, then we would be able to do this. Right? So for the rest of class, I am going to build the technology or code required to make this work. Okay? Pictures now, okay? Because what we now need to do is describe this enough. Now, did I not describe state transformer summary here? Okay, well, it doesn't matter. Okay, so I'm going to draw some pictures for you. They're taken from Hutton's book, but I'm not sure Hutton gets to like claim that these pictures are his inventions. It's a very typical way of describing black box computation. So let's look at this picture, and I'm going to tell you how to interpret it. Right? I'm saying, here's a state transformer. I don't care what it does. What happens is state goes into it, and new state comes out of it. So like our fresh function, 7 goes in, 8 comes out. Right? And then 8 goes in, and then 9 comes out. Right? That's how that would work. Okay? So this is how we interpret this. This is a state transformer. We don't care what it does, but a state goes in, and a new state comes out. That's it. Enough of understanding of it, because I'm just going to make this picture arbitrarily more complicated. So if at any point something in the picture doesn't make sense, you stop me. But this should be easy. Right? A state transformer is just anything that takes a state, gives you back a new state. We want more than that. Right? So what I really want is a state transformer which, given state, returns output and returns a new state. Right? That was sort of like the last tree function, right? I said, oh, starting with state 0, then it was able to give me a labeled tree and a fresh value. Okay, so this is a state transformer which takes a state and gives out outputs into new state. Okay, one more complication, and we're going to get the real state transformer. This is what we're going to be working with when I build the state transformer. And this is what it takes as input, and this is what it takes as output. But the order here matters. So this picture is meant to describe the following computation or execution or evaluation. X goes in, and then the state transformer becomes a state transformer. Right, so X goes in, you get a state transformer from that, then you give it a state, and out comes output, which is normally like f of x. Right? Inside here is some f that's operating on x, and s prime, a new state. Right? So this is how all of our state transformers are going to work. You give me something from A, I become, and then I return to you something like this, in which case I expect to get a state, and I'm going to return to you back output and a new state. Okay, so that is the basic state transformer. Let's see if we can code that up now. Oh, so what we are also able to, so these state transformers are just functions, right? And we should be able to compose functions. So here's a picture of how you can take two state transformers and simply like glue them together to get like one other state transformer, right? So if you have two state transformers, the first one takes x and becomes a state transformer. That takes a state s, and y and s prime come out of the first state transformer. Y then gets plugged into here. You get back a state transformer. A new state goes in, and you get output and that state. Right? So but it doesn't matter. All I want to designate here is that, yeah, if you have two of these, the composition is very clear. Right? And then I don't really care about what's happening on the inside. We just sort of abstract that away. Right? So you can, if you have a state transformer, you can always sort of compose them with one another. Oh, none of this is on your exam, by the way. I should mention that. This is a tricky thing to understand, these state transformers. I'm not asking you basically any questions about them on your exam. We should still engage with it because they're critically important for doing I/O. I/O is on your exam, but like it's not critically important that you understand all of this. Okay. Okay, so let's code up everything that like I now want this, but as Haskell code, not as a picture. Okay, so to simplify we have this s coming in and s prime coming out. And what does s mean? State. And that's really could be anything. To simplify everything, we're just going to say state is an integer. That's enough. As soon as state's an integer, that means state can be anything that's countable. Right? So like from theory, this is not really going to mess things up. And states are usually numbered anyways, right? If you've taken 2504, we're like moving from state to state, these states are numbered. So this is a very sensible simplification to make, saying like, look, integers. We're just going to assume that state is an integer. So whenever you see state here, you just think integer. Okay, so what does it mean to be a state transformer? Well, I said a state transformer is something that takes state and returns to you output and state, right? So that's what this is. All right, a state transformer over A is a function that takes state to a tuple of output and new state. Okay, so let's do fresh. I said fresh should be able to be a state transformer. So I'm saying, okay, fresh is a state transformer over integer. So what does that mean? It means I should be able to take state to integer state, but really it's integer to integer tuple. So here's how I can define it. Right? So I'm saying fresh is a state transformer. Well, that means I have to make fresh a function, and it's a specific function that takes a state to a output and a new state. And in this case, the output is the fresh integer. So this is how this could work. The first state is 0. What's the next state? Well, I give this state as input to the fresh state transformer, and output comes out, which I'm claiming to be a new integer, and the next state that has to be threaded back in. I then thread the new state back to fresh. I get out a fresh integer and the next starting point. I then put that in, and I get back a fresh integer and a new starting point. Right? The function always says, tell me where to start, and I'm going to tell you where to like keep going from. That's how you can sort of see this like state being passed and forth. And what is it the case that fresh x, fresh y, fresh z are here? Like unique integers. Right? They're always new. Right? So as long as you're always calling fresh with the thing that it passed back to you, you're always going to get a new integer. This is like almost like the concept of self in an object in Python or Java, right? That you almost have a self-reference. It's just that like I'm actually passing that self along to the next thing. Any questions? No? Because like really, like don't try to overcomplicate this, right? A state transformer over A is just something that you give an integer, and you get output and a new integer, like the next state. And you're always obligated to go and put it back, which is the thing we'll automate. OK, so I said I want to make the state transformer an applicative, a monad, a functor. But we can't do this with types. Right? So I have to make the state transformer a new type. And the obnoxious thing about new types is you have to use these like dummy constructors. OK, so we're going to have a state transformation. It's a new type. And instead of just being a function, it's a function with this S decorator on it. It's just a little bit, it's a dummy constructor. I don't know what to say. OK, so because we have this dummy constructor, I'm going to define a function called apply, which if you give me a state transformer and a state, I can just go ahead and apply the state to the state transformer. And this will just automate removing the dummy variable and putting it back on. OK. So what I want to do now is like given this type, okay, I actually want to now go and define its functor instance, its applicative instance, its monad instance. And as soon as we can define the monad instance, then we're off to the races with some of this stuff. So, okay, let's try. I'm going to try doing it in two ways. So we'll get rid of all of that. So there's my new type. Here's our apply routine. Here's the apply down here. OK, and let's just do some sanity checks. Let's try to make our fresh function. And I want this to be a state transformer over integer. So fresh has to be a function with this S decorator on it that given a state returns an answer in the new state. Well, the new state is just going to be state plus 1. And funny enough, what we want to return here is state. OK, so let's do this. Whoops. Did I not define state? Apply. Oh, state here. Type state is just an integer. OK. So now I can say I have fresh. I want to apply to fresh 1. And we should get back out 1, 2. Wrong way. Did I not load? Anyone see my mistake? Fresh. I should be able to, that should work. Haskell's wrong. No, there has to be some, I can do it from the REPL? Apply fresh 1. Oh. OK. I guess I would have had to assign it to something. Yeah, OK, anyways. So so this is how I sort of use, so fresh is a state transformer. And I'm saying, OK, give it the state 1. And what it gives back is it's saying, OK, 1 is the fresh integer that you should use. And 2 is like the new starting state the next time you call me. So like the next time I would call fresh would be like this. And like the monad is what we're going to, is automating this threading, right? From a high level perspective, that's what's happening. OK. So this is the functor now for that state transformer. And I'm going to describe it in picture and then show you that it just corresponds to like the code that I've put up there. So what does it mean? So what is the structure in this case? Well, the structure is ST, the state transformer, the thing that turns type A into something that's a function going to tuple type A integer, right? So clearly, we want to jump in. That's the structure which we want to change inside of, okay? So all I'm going to do for the functor on a state transformation, you have a state transformation, it spits out outputs and a new state, and it's this output actually which I just want to change. Right? So if you give me a state transformer and G, right? So remember fmap has to have this type. Right? So here it should be, you give me a function that goes from A to B and a state transformer that's going to spit something out with A, and I'm going to give you a state transformer of something that spits out with B. Well, here's our state transformer that spits out something of type A. I'm just going to send it through G. Gx now is of type B. So what is this whole thing now? Well, it's a state transformer, which is a state transformer over type B, because that's the thing coming out now. This is B. Type B, this is type A. Right, so this is what it means to map over a state transformer. You get a new state transformer, which spits out something type B instead of type A. Yes, no, maybes? OK, so if you believe this picture, now it's just like I just have to show you how to that the code actually corresponds to it. So what does this picture say? Well, OK, so the function is called G. The state transformer is called S of t. So what do I need to do? I need to apply S to S of t and grab X and S prime. Have I done that? Yeah, apply S to S of t and grab X and S prime. We got it. Now I need to put G over X and return it with S prime. Well, that's just this. Right? G of X, S prime, and that's the thing I want to return. Right? That's what's coming out, a G of X and an S prime. Does that make sense? This has to make almost crystal clear sense because the next one is the applicative. Right? Well, OK, pure. But that's what we're going to have to talk about next. So let's try and figure this one out. OK? Questions? Or are you telling me that this is clear? Which I would be skeptical of that, right? Yeah. S is an integer necessarily. X is A. Right, so maybe you think it's an integer because of this fresh example, right, where I made it an integer, but it could be anything. Yeah. So in our tree example, what was coming out was a tree and an integer, right? And in that case, A here was tree of A. Yeah? OK. S prime isn't the state transformer. S prime is an output, right? Yeah, that's the next state. So in tuples, we can map over tuples, right? Does everything in the tuple change? I believe only its last position changes in the tuple. So we're not necessarily want to map over everything. So remember, that's the structure is encapsulating A here. So A is the thing I want to change, right? ST sort of hides away the fact that we're returning this tuple, right? So the structure itself is yeah, this is almost like A is the second position of its tuple. Maybe I shouldn't have put it in the first, but that's how it's been defined. OK, so this is a functor, and I can take this, OK, and that should be OK. One, two. Cool, right? It's fine. This is a functor for state transformer. Let's keep going. All right, so applicative. This one is easy. What does it mean to put structure over something, right? That's given A, how do you make a state transformer over A? Well, that's easy, right? Here's a state transformer. You put in X, X comes out. So that's the identity. And you put in S, and S comes out. It's just nothing happens, right? But if you give me anything of type A, I just have to sort of wrap it, right? What does this mean? You give me something of type A, and I return to you a state transformer. And a state transformer is this function which takes a state to output and a state which has this dummy constructor in front of it. So that this is exactly executing this. Does that make sense? Because remember, I said in order for the thing in the box to become a state transformer, it first has to take x as input. That's exactly what this is doing. First you give me x, then I can give you back a state transformer. Right? Because usually the thing coming out of the state transformer is some function over x, although in this case it's this is the identity. Okay? But this is how you put structure over anything to make it a trivial state transformer. Any questions about that? Okay, so now we have to do the applicative. Okay, so remember the applicative has this type. You need to give me a state transformer over a function and a state transformer over A, and I will return to you a state transformer over B. So this is hard. This is going to be harder than the monad, but let's study it. Okay? So let's say that this is a state transformer over a function. That's this. The second input is a state transformer over A. We're going to call that this. And what I have to give back is a state transformer over B, and I claim that's what this whole thing is. Right? So to take a state transformer F and to applicatively map it over the state transformer of X is this picture. Okay, and it's hard to give any type of intuition about this because I'm just writing something so that the types work out, which is like often just what we're doing in Haskell. I don't know what I'm programming. I'm just trying to make the types work, and then suddenly Haskell magic works. Okay, but how can we tie these two things together? Like given a state transformer encapsulating a function and a state transformer encapsulating something from the domain of that function, what do I do? Well, so I give this state transformer F S, a state. I give it state. Out of that should come out output and a new state. Let's call that output F and S prime. Right, so I'm going to apply to the state transformer that's encapsulating the function this state, and F and S prime come out. That's this. Now I want to take S prime and I want to apply that for the state transformer for X. And I'm going to get X and S double prime out. So that's what I'm doing here. Apply to the state transformer of X, S prime. And from that get the new state and output. So that's this and that. And then what I want to do is take F and actually, the F that was trapped in this structure, and actually apply it, or to X, which is coming out of here. But I do have F, I've managed to extract that. I do have X, I've managed to extract that. Therefore, I can do this. Right, so if X was of type A and F was type A to B, this is now B. And S double prime, that comes out. So that's a state transformer over B. Okay, so that's this code faithfully implements this picture. And see all these primes? What does this look? Remember the fresh example we're doing at the beginning of class? This is what's going to automate that. Right? This is doing one level of threading for you, and we're going to abstract that away. I don't want to have to do this every time, but this is effectively what's happening, is this passing of the new state back in. Okay, so that's the applicative. Let's copy paste this. 1, 2. 1, 2. And boosh. Huh? Did someone say, oh, I think I have to go out further. Oh, and pure. I have to get pure in here. Okay. Just to prove to you that like all of this stuff is typing properly. Okay, so I've defined a functor that types properly. I've defined an applicative that types properly. Yeah. So could we swap these two? Probably, yeah. I'd have to think. I'd have to think about if the behavior is, if the typing would still work out. I don't know if the behavior would still be the same, because it's like switching. I think it may, yeah, like you could switch it, but you would definitely get different output because the threading would happen differently. It's like in the fresh labeling example for the tree. I labeled the left, then right. If I changed that, you'd actually get a different labeling. And I believe that would be the same effect for swapping those two things on in the middle. Okay. This is the monad. This is actually easier than the applicative. So what do we do in our monad? Well, remember, we need something that's a state transformer over A. State transformer is the wrapper of all of this. Then you need to give me a function that, given A, gives me back a state transformer over B. And then I can give you back a state transformer over B. So let's see if we can indeed construct a state transformer over B given this information. So ST is the state transformer over A. So it takes in S, and it gets back something X of type A. It also spits out S prime, and since, where is my F? Yeah, F is here. So this one isn't a state transformer. I probably shouldn't have drawn that big box, but F is going to map that X, and it's going to, yeah, this is a little bit troubling. So F takes X and becomes a state transformer, right? But that's what I said we have to interpret. Remember back here? I said if I draw this box, you have to interpret this as X goes in, and then you get a state transformer, which can take S. We are seeing exactly that at play here. X needs to go into here. And then F takes it, it's of type A, and then becomes a state transformer over type B. That's what this type is. Give me A, and I will become a state transformer. Right? This thing spat out A that goes into here, which becomes a state transformer over B. And then we have a state transformer over B, which is the thing that I've written. Right? So let's look at this. Right? A state transformer over A, and a function that takes something from A and makes you a state transformer of B. What do I want to do? Well, I want to apply to this state transformer this state. I'm going to get out of it X and S prime. That's what this is. And then what I want to do is just take F of X. That becomes a state transformer over B, and I want to put S prime through it, right? Because what will be spat out here is some output and something of type B, right? So this is a function that gives us give me a state, and I'm going to return to you something that's B, right, and the new state, I guess. Okay, so I'm going to copy paste this. Like, you will have to go stare at this a bit, but again, it's not necessary that you understand any of these pictures. It is sufficient that you're like, I believe they form functors, monads, and applicatives. I believe now I can use the do notation. I don't quite understand what's happening, but I can use the do notation. And my philosophy of saying we can just rip structure out of stuff, that is sufficient. Okay, so I'm going to write that here. What is happening? 1, 2. Oh, 1, 2. Okay. I am missing something here. 1, 2. Okay, right, so I have this new type for state transformation. I've made it a functor, I've made it an applicative, I've made it a monad. So now my claim is that we should be able to solve the fresh labeling problem now using these new forms. Okay, so let's think about this. So I want to use fresh somehow. Where's our old okay, so there's my tree. I thought I had a tree. Let me go get a tree. I must have deleted it here. Okay, so here's a tree. Okay, so now I want to write this label routine, which goes from tree of integer, tree of A to tree of integer, where my tree now has these unique labelings. So I want to be able to use, I want to use my applicatives, and I want to use the applicative and the functor first, and then we'll use the monad. So what does it mean if this is a leaf? Or do I have to break this up? Yeah, what should we do if this is a leaf of X? We have to be more clever. Okay, sorry, I'm not doing this properly. Okay, so I want to have this where I want to actually have a state transformation over the tree of integers. I believe that's the case. Sorry, guys. Right. Okay. So I'm going to modify this a bit, right? I'm going to say, okay, give me a tree, and I'm going to perform a state transformer over that tree and give you back a tree of integers, right? This is basically the thing saying, hey, you're a data type now that has a global variable, persistent state. That's effectively like giving it a global variable wrapper or like an object wrapper. And this one's still opaque, but I/O won't be, right? That's the issue here. Okay, so we have a state transformer over this, which effectively means what are we returning, right? It's something that, given a state, will return to us back a labeled tree in the new state, okay? So given a leaf, how can I get a state transformer over tree of int? Right, so I have, let's think about the typing here. We have tree of A. I want to get a state, like how do I go from tree of A to state transformer tree of integer? Okay, let's think more. We have fresh, which is this. Yeah? Well, okay, again, I want to use a functor. Okay, so I want this. I have this. How can I get from this to this? What? Yes. Label with a fresh integer. That's what this means, right? I can show you that that will work. Oh, sorry, was it leaf? Capital, yeah, yeah. Right, so this should be working already. Let's try to label a leaf of A. Oh, first, yeah. Does my tree not have a show of instance of show? Why can't that show? Oh, no, yes, of course, of course. Yes, I have to apply 0. Huh? This is why I should never code this lecture. Okay, so if I give this back, I should get a state transformer. So this is a state transformer. And I should be able to apply to that state transformer this. Oh, okay. Yeah, okay, great. Yeah, because it needs to know where to start, right? So let's keep going then. So what does it mean to label a node tree left, tree right? So what do we need to come out of this? Right, tree of integer, right? So what's t left and t right? So we have well, I want to start thinking, it's just hard to guide everyone to the solution here without just giving it, right? Okay, so there's an applicative form here. We clearly have to map something, TL, T right. But what should that mapping be? So we could try to work through the typing information here. I think I'm running out of time. Yeah, that's a node. Because I'm saying go and perform sorry, should be label. Label that label that. Saying label the left tree, label the right tree. You're going to give me back a state transformer for both of these things. And I'm saying tie together those state transformers by mapping over node, which is the thing that has to connect them back together. So I'll show you we'll do this. That will work. So I should be able to, here's tree. I should be able to say label T. That's going to be a state transformer. I should be able to say, OK, since you're a state transformer, apply that state to it. Right? OK, so I know it's, this is a hard lecture. I'm not going to try and pretend that we're all going to understand this. Right? It was a tough proposition for me to explain something like this in 2 hours. But go home and read it. We'll talk about it again next week after you've been able to stew in it a bit. But we only really need to be able to do stuff like this and not really. So we do have some exercises to help flesh this out. Here's S. It's a more complicated one. Let's just do that again. Right? So apply this label to S. Fresh labels again. OK, so this is called the applicative form. But let's try to do this now with like the monad instead. Right? Because maybe that would be more clear. Right? So the monad gives us access to the do notation, correct? So actually, I think this one, OK, let's just do them all. No, I think we should probably leave this one like, let me think. Should we? Oh, let's leave leaf for the moment. How can we use do here? So what do I want? I want you to label that tree. OK, but you're a state transformer. I don't want the state transformer. I want the tree. OK, extract it. Remove the state transformer wrapper. Just get the get the tree. OK, label the right tree. But this returns a state transformer. I don't want that. OK, pull it out. And just give me the tree. And then connect them. And then put the structure back. Oh, jeez. Yes? OK. All I want is to be able to understand this notation. If none of this lecture really matters, but it just matters because, OK, I don't want to sweep this all under the rug. I defined a new type for state transformations. This new type allowed us to imbue any function with the capacity to remember. That's important. OK, and because it has the capacity to remember, we have to play this game of always saying, if I want to remember, you have to tell me where to start, and I'll just tell you where I ended. And then you have to give that back to me. And it's like, oh, but we can automate that using some of the functors, monads, and applicatives. And I said, I did that. Right? It's here. It types. It's working. If you want to understand what these things are doing, study the picture. If you don't care, if you believe me that it's working, great. Then all you need to understand is that we now have a do notation. And the arrow is the thing that allows us to extract something from structure. And this is really important because I/O is structure that is opaque. Right? And with do notation, we'll be able to reach through the I/O structure and do stuff without leaving I/O. Right? There's a huge, it's almost funny how we made I/O pure. It's funny. I/O is a state transformation. How much information do you need to know to perform the exact same state transformation again? Because what's the problem with I/O, right? You don't know what's happened. There's like side effects. But what if I'm like, do some I/O, and here's the bit setting of every bit on the computer? Or worse than that. Do this I/O, here's the position of every atom in the universe. Okay? So under that condition, if I/O is a state transformation, you're literally giving me every position of atom in the universe, then yeah, I can repeat that I/O computation. It's functionally pure. So when we do our I/O lecture, I'm going to say I/O is a state transformation over the entire universe. You give me the entire universe, I'll do a computation, give you output, and the new state of the universe. Okay? Do you think we'll be able to hand over the position of every atom in the universe? No, yes. No, we're going to be doing this almost theoretically. Okay, hold on. I'm not actually through these slides yet. Okay, there you have that. You can do this if you want. If you're getting bored, go ahead and try to prove some of these things. Next week is I/O. Next week is Hello World example. But okay, again, I want to, what happened? Did we lose? Okay, I think we're still saved because there's an echo recording. And I can pull that echo recording and put it to YouTube, but it's not going to be. What happened to the slides?